Welcome! In this session, we'll explore an exciting problem number 1358, number of substrings containing all three characters. We'll break down the problem, analyze approaches, and learn how to solve it efficiently. Let's get started. In this problem, we are given a string S that consists only of the characters A, B, and C. The task is to determine how many substrings of S contain at least one occurrence of each of these three characters. A substring, as you know, is simply a contiguous sequence of characters within the string. For example, in the string ABC, the substrings include A, B, C, UB, BC, and ABC. The goal is to count all substrings that have at least one A, one B, and one C. The input string S can be anywhere between 1 and 100,000 characters long, and our output will be a single integer representing the count of these valid substrings. This means we need an efficient approach to solve this problem without explicitly generating all possible substrings, as that would be computationally expensive. For instance, consider the example where S is equal to AppCap. The output for this case is 10 because there are exactly 10 substrings that contain at least one A, one B, and one C. These substrings are ABC, AppCa, AppCab, AppCap, Cab, Cab, and the second occurrence of ABC. Notice that some substrings are of varying lengths, and the same substring can appear multiple times in the count if it occurs in different positions within the string. This demonstrates that we need to account for all possible valid substrings, not just unique ones. Now, let's look at another example where S is AAP. Here, the output is 3 because there are only 3 substrings that contain all 3 characters, AAP, ACP, and ACB. The key difference in this example is that the string starts with multiple A characters, so the shortest valid substrings containing A, B, and C only appear near the end. Similarly, for the string ABC, there is only one valid substring, which is the string itself, ABC. This is because the shortest possible string that contains all 3 characters is exactly 3 characters long, and in this case, there is only one such occurrence. To summarize, the constraints of the problem ensure that the input string S will only consist of the characters A, B, and C, and its length can go up to 100,000. This means that any solution must be optimized to handle large inputs efficiently. Additionally, edge cases to consider include strings that are too short to contain all 3 characters, such as A or AAA, which would result in an output of 0. If the string is exactly ABC, the output is 1 since it is the only valid substring. For longer strings, the solution must count valid substrings systematically without explicitly generating all possible substrings to avoid performance bottlenecks. These constraints highlight the need for an efficient algorithm to solve the problem within the given limits. To begin, the brute force approach relies on a straightforward but computationally expensive strategy. The idea is to examine every possible substring of the input string S and check if it contains at least one occurrence of the characters A, B, and C. This involves iterating over all possible starting indices and, for each starting index, iterating over all possible ending indices to generate substrings. Each substring is then checked for the presence of all 3 characters. While this method is simple to implement, it has a cubic time complexity of O, n cubed, where n is the length of the string. This is because generating all substrings takes O, n squared, and checking each substring for the required characters takes O, n. Although it works for small input sizes, it is highly inefficient for larger strings, making it impractical when n is large, such as 10 to the power of 5. The trade-off here is that while the logic is easy to grasp, the execution time quickly becomes prohibitive as the input size increases. Now, moving to an improved method, the sliding window approach with a hash map provides a significant boost in efficiency. This technique uses 2 pointers to define a window in the string and dynamically adjusts the window size to ensure it contains at least one occurrence of each character A, B, and C. The right pointer expands the window by including more characters, while the left pointer contracts it to maintain the condition. A frequency map is used to track the counts of these characters within the window. Once all 3 characters are present, we can calculate the number of valid substrings that start at the current left pointer and extend to or beyond the current right pointer. This is computed as n right, where n is the string length. This process continues until the right pointer reaches the end of the string. The sliding window approach is highly efficient with a linear time complexity of O, n, as each character is processed at most twice, once when expanding the window and once when contracting it. Additionally, it uses constant space, making it an excellent choice for large inputs. However, it requires precise handling of the pointers and frequency map to ensure correctness. An alternative optimized approach involves using prefix sums to solve the problem. Here, the idea is to pre-compute the cumulative counts of the characters A, B, and C up to each position in the string. These prefix sums allow us to quickly determine if a substring satisfies the condition by comparing the differences in counts between two positions. For each position in the string, we calculate the earliest point where the cumulative counts of all three characters make the substring valid. This enables us to determine the number of valid substrings ending at the current position. The prefix sum approach has a time complexity of O(n), as it processes the string in a single pass, and a space complexity of O(n), due to the storage required for the prefix sums. While this method is efficient and relatively straightforward to implement, it requires additional memory for the prefix sum arrays, which may be unnecessary given the sliding window solution. This trade-off makes it a less appealing choice when space is a critical consideration. The sliding window with a hash map is selected as the primary strategy due to its balance of performance and simplicity. Unlike the brute force method, it avoids redundant checks by dynamically resizing the window to include only the necessary characters. The insight that any substring starting at the current left pointer and ending at or beyond the current right pointer is valid allows us to avoid explicitly checking every possible extension. This reduces computational overhead significantly. Compared to the prefix sum approach, the sliding window method is more space efficient, as it requires only a constant amount of additional memory. While both approaches share the same linear time complexity, the sliding window approach is easier to implement and debug. On the other hand, the brute force method is excluded because its cubic time complexity makes it impractical for larger inputs, and the prefix sum approach is not chosen due to its higher space requirements. This makes the sliding window strategy the most effective and scalable solution for the problem. Each approach comes with its own set of trade-offs. The sliding window method is optimal in terms of both time and space complexity, making it the best choice for solving this problem efficiently. However, its implementation requires careful attention to detail to ensure correctness, especially when managing the movement of pointers and updating the frequency map. The prefix sum approach, while slightly less space efficient, can be easier to debug in some scenarios due to its reliance on pre-computed sums. Finally, the brute force method, while simple to understand, is only suitable for small inputs due to its prohibitively high time complexity. In conclusion, the sliding window strategy stands out as the ideal solution for balancing efficiency, simplicity, and scalability, making it the most practical choice for this problem. To solve this problem, we need to find all substrings in a given string that include at least one occurrence of the characters A, B, and C. A straightforward way to approach this is by using a brute force method. First, we initialize a variable count to 0, which will keep track of the number of valid substrings we find. Then, we use two nested loops to iterate over all possible substrings. The outer loop sets the starting index I of the substring, while the inner loop determines the ending index j. By generating all possible substrings in this way, we can systematically check each one to see if it meets the criteria. For each pair of indices I and j from the nested loops, we extract the substring from S, I, to S, j. Once we have the substring, we check whether it contains at least one A, one B, and one C. This can be done by iterating through the characters of the substring and counting the occurrences of these three letters. If the substring satisfies the condition, we increment the count variable. After examining all possible substrings, we return the final value of count. However, this approach is not efficient. Generating all substrings takes O(n) squared, and checking each substring for the required characters can take O(n), leading to an overall time complexity of O(n) cubed. To address this inefficiency, we can use an optimized approach based on the sliding window technique. The sliding window approach allows us to dynamically adjust the range of substrings we consider, making the algorithm much more efficient. We start by initializing a dictionary frequency to keep track of the frequency of A, B, and C within the current window. Additionally, we set two pointers, start and end, both initialized to 0, to define the bounds of the sliding window. A variable count is also initialized to 0 to store the number of valid substrings. Next, we expand the window by incrementing the end pointer. For each character at S end, we update the frequency dictionary to include its count. Once the window contains at least one A, one B, and one C, we know that all substrings starting from start and ending at or after end are valid. This is because extending the window further will continue to include these three characters. At this point, we calculate the number of valid substrings within the current window. Specifically, substrings starting from start and ending anywhere from end to the end of the string are all valid. This count can be determined by adding len, s, n to the count variable. Once the valid substrings are counted, we try to contract the window by incrementing the start pointer. As we move the start pointer forward, we decrement the frequency of the character at S, start, in the frequency dictionary. If the window no longer contains at least one occurrence of A, B, and C, we stop contracting and continue expanding the window using the end pointer. After the loop completes, we return the count variable as the total number of valid substrings. This approach achieves a time complexity of O, n, as both pointers traverse the string linearly. Several key data structures make this optimized approach efficient. First, we use a dictionary, or hash map, to store the frequency of A, B, and C within the current window. This allows us to perform updates and lookups in constant time. Second, the two pointers, start and end, define the sliding window and enable us to dynamically adjust its size without recalculating the entire substring or its properties. Together, these data structures ensure that we only traverse the string once, making the algorithm both time and space efficient. When applying this algorithm, it's important to consider edge cases. If the string has fewer than 3 characters, it's impossible to form a valid substring, so we immediately return 0. Similarly, if the string does not contain all 3 required characters, A, B, and C, the result is also 0. Another scenario is when all characters in the string are identical, such as AAA, where no valid substring can exist. Finally, the algorithm handles mixed distributions of A, B, and C efficiently, ensuring that all valid substrings are counted regardless of their order or frequency within the string. This implementation uses the sliding window technique to efficiently count substrings containing at least one occurrence of each character A, B, and C. The algorithm initializes 2 pointers, left and right, which define the boundaries of the sliding window. A dictionary frequency is used to track the count of A, B, and C within the current window. The variable count keeps track of the total number of valid substrings. The right pointer iterates through the string. For each character at position right, its frequency in the frequency dictionary is increment. Once the window contains at least one of each character, A, B, C, the algorithm calculates the number of valid substrings ending at right. This is done by adding the number of substrings starting from the current left to the end of the string, len, s, right. To ensure the window remains valid, the algorithm shrinks the window by incrementing the left pointer and reducing the frequency of the character at the left position. This continues until the window no longer contains all 3 characters. The sliding window approach ensures that each character is processed at most twice, resulting in an efficient O, n, time complexity. This makes the solution optimal for large input strings while maintaining clarity and correctness. This is the Java implementation of LeetCode problem number 1358, number of substrings containing all 3 characters. The logic mirrors the Python implementation using a sliding window approach. Key differences include using an integer array to track character frequencies and Java-specific syntax for looping and accessing characters. The solution efficiently calculates substrings by leveraging the sliding window technique. To solve this problem, we'll use a sliding window approach. Starting with the input string s equals appcap, the initial state is defined with left at 0, count at 0, and the frequency map frequency initialized to track the counts of A, B, and C is 0. As we iterate through the string, the first window is formed with right equals 0, where the character is A. We update the frequency map to reflect the presence of A, so frequency becomes A, 1, B, 0, C, 0. However, the window does not yet contain all 3 characters. Proceeding to right equals 1, where the character is B, we update the frequency map again to A, 1, B, 1, C, 0. Still, the window does not include all 3 required characters, so we continue expanding the window to find a valid substring. Next, at right equals 2, the character is C. Updating the frequency map gives us frequency equals a1, b1, c1, and now the window contains all three characters a, b, c. At this point, we calculate how many substrings can be formed starting from this window. This is determined by adding len, s, right, which is 6, 2 equals 4, to count, making the current count 4. To explore further substrings, we shrink the window by decreasing frequency, a, to 0 and moving left to 1. Moving to right equals 3, where the character is a, the frequency map updates back to a, 1, b1, c1. Again, the window contains all three characters, so we add len, s, right equals 3 to count, making the total count 7. We then shrink the window by decreasing frequency, b, to 0 and moving left to 2. This process continues for right equals 4 and right equals 5, eventually resulting in a final count of 10 substrings that contain all three characters. Now let's consider another example with s equals a. We initialize the sliding window variables as before, left equals 0, count equals 0, and frequency equals 0, b, 0, c, 0. As we iterate, the first three characters, all are encountered at indices right equals 0, right equals 1, and right equals 2. The frequency map updates progressively to a, 1, a, 2, and a, 3. However, the window still does not include all three required characters. At right equals 3, where the character is c, the frequency map updates to a, 3, b, 0, c, 1, but we still haven't formed a window that contains all three characters. We need to expand the window further to find a valid substring. Finally, at right equals 4, the character is b. Updating the frequency map gives us a 3, b, 1, c, 1, and now the window contains all three characters a, b, c. At this point, we calculate how many substrings can be formed, adding len, s, right equals 5, 4 equals 1 to count, making the current count 1. After this, we shrink the window by adjusting the frequency map and incrementing left. However, no further valid substrings can be found, so the process ends here. The final count for this example is 1. In the third example, with s equals ababab, we begin as usual with left equals 0, count equals 0, and the frequency map initialized to a, 0, b, 0, c, 0. As we iterate through the string, the window alternates between a and b, but it never includes the character c. Since a valid substring containing all three characters cannot be formed, the output for this example is 0. The time complexity of our solution is O, n, where n is the length of the input string. To understand this, let's break it down. First, the outer loop, which moves the right pointer from the start to the end of the string, iterates exactly n times. This contributes O, n, to the total complexity. Then, we have the inner while loop, which is responsible for shrinking the window by moving the left pointer. While it might seem like this could add significant complexity, each character is only added to and removed from the window once over the course of the algorithm. This means that, in total, the left pointer also moves at most n steps, contributing another O, n. Finally, the operation where we add the count of valid substrings is a constant time operation, O, 1, and does not impact the overall complexity. Combining these, we get O, n, from the outer loop plus O, n, from the inner loop, resulting in a total time complexity of O, n. The space complexity of this solution is O, 1, and here's why. The primary data structure used is the frequency dictionary, which keeps track of the counts of the three characters, a, b, and c, within the current window. Since the dictionary only ever holds 3 keys, the memory usage remains constant regardless of the size of the input string. This contributes O, 1, to the space complexity. Additionally, the algorithm uses a few integer variables, such as left, right, and count, which also consume a constant amount of memory. There are no other data structures or allocations that scale with the size of the input. As a result, the overall space complexity of the solution is O, 1, making it very efficient in terms of memory usage. To appreciate the efficiency of the sliding window approach, let's compare it to a brute force solution. In a naive approach, we would generate all possible substrings of the input string and check whether each substring contains all 3 characters, a, b, and c. Generating all substrings takes O, n squared, time, and for each substring, checking the presence of the 3 characters would take O, n, in the worst case. This leads to a total time complexity of O, n cubed. Additionally, if we store these substrings or intermediate results, the space complexity could go up to n squared. The sliding window approach, however, improves on both fronts. By traversing the string linearly with the right pointer and managing the window efficiently with the left pointer, the time complexity is reduced to n. Furthermore, the use of a fixed-size dictionary and a few variables keeps the space complexity at 1. Clearly, the sliding window approach is far superior in terms of both time and space efficiency. When analyzing the best, average, and worst cases, the time complexity remains n in all scenarios. This is because each character in the string is processed at most twice, once when it is added to the window by the right pointer and once when it is removed from the window by the left pointer. This results in a maximum of 2n operations, which simplifies to n. Additionally, the constant time operations within the loop do not affect this asymptotic complexity. To confirm this mathematically, we can see that the algorithm's work is directly proportional to the size of the input, and no additional factors cause it to deviate from linear time. This consistency across all cases makes the algorithm optimal, with time complexity of n and space complexity of 1. When tackling this problem, there are several common mistakes to watch out for. First, ensure you handle edge cases with very short input strings, like those of length 1 or 2. Neglecting these can lead to runtime errors or incorrect results, so always test these edge cases explicitly. Next, avoid generating all possible substrings explicitly in a brute force manner, as this can result in n cubed time complexity, which is impractical for large inputs. Instead, optimized approaches like sliding window or two-pointer techniques are much more efficient. Another frequent issue arises from overlooking repeated characters in the input. For example, strings with multiple occurrences of the same letter can lead to counting errors unless you carefully track character frequencies. Additionally, incorrect bounds in the sliding window approach, such as failing to adjust the window size correctly or not updating the frequency table properly, can easily result in off-by-one errors. Finally, don't ignore constraints or edge cases involving non-alphabetic characters. If the problem specifies lowercase letters only, be sure to validate or clarify this constraint during interviews to avoid unnecessary errors. Mastery of the sliding window technique is critical for solving substring problems efficiently, and it's a skill interviewers often look for. This approach is highly adaptable to problems with varying constraints, so practice implementing it in different scenarios. Additionally, aim for optimal solutions with linear time complexity, as brute force approaches, while functional, are unlikely to impress in an interview setting. Interviewers often probe for ways to optimize, so being prepared to discuss how you achieved n complexity is essential. Another key tip is to clarify any ambiguities in the problem. For instance, confirm whether only lowercase letters are allowed or if overlapping substrings are permitted. This not only ensures you're solving the right problem but also demonstrates good communication skills. Finally, working through related problems can help you recognize reusable patterns. For example, problems like longest substring without repeating characters, minimum window substring, permutation in string, and find all anagrams in a string all involve similar concepts like substring manipulation, character frequency tracking, and window adjustments. By practicing these, you build a strong foundation for tackling any variation of this problem. There are also alternative approaches you can explore to solve this problem. The two-pointer method is a great option, as it reduces time complexity to n. However, it requires careful management of the character frequency map to ensure correctness. This method is especially useful when dealing with large input sizes where brute force solutions would be too slow. Another effective strategy is the combination of a hash map with the sliding window technique. While this approach uses slightly more space, 26, for the frequency map, it ensures optimal linear time execution and works well when constraints are based on specific characters or patterns. Lastly, there's the brute force approach, which is simple to implement but highly inefficient, with an n cubed time complexity due to the explicit generation and checking of all substrings. This method is only practical for very small input sizes or as a baseline to verify the correctness of other, more optimized solutions. Each of these approaches has its trade-offs, so understanding when to use each one is key to solving this problem effectively. Great job! To recap, we tackled the problem using efficient techniques like sliding window and discussed key optimization strategies. Keep practicing and applying these patterns to similar problems. Thanks for watching, see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!